So welcome to the last session of the analysis seminar this fall semester. We have two talks today. The first talk is by Ryan Gibara at the Université Laval. He'll speak on boundedness continuity of rearrangements. Welcome, Ryan.
Thank you very much. First of all, thank you, whoever has decided to attend my talk. For those of you who attended my CMS talk earlier this week, it's going to be very similar, but hopefully the extended time will mean that it'll be much better talk. That's the overall goal. So very first thing I have to say is that this is joint work with Almut Burchard at University of Toronto and Galia Dafni at Concordia. They were my PhD supervisors. Almut Burchard is an expert in rearrangements and geometric analysis. Galia Dafni is an expert, as you all know, I hope very well, in harmonic analysis. And so my being their PhD student, I'm supposed to know a little bit about both. And so this project is about boundedness and continuity of rearrangements on specifically spaces defined by mean oscillation. So we're trying to merge these two worlds, the world of rearrangements and the worlds of harmonic analysis, but specifically BMO and spaces defined by mean oscillation. So the first thing I have to start off with is what is BMO, bounded mean oscillation? If I take a locally integrable function, an Rn, I say it's in BMO if this quantity, the BMO norm, is finite, where I'm looking at the deviation of a function from its mean, f sub q, on a cube with sides parallel to the axis q. I'm taking the average, that's what this integral with the bar means, the average of this deviation from the mean, and then taking the supremum over all cubes. So literally bounded mean oscillation. It goes quite nicely in order in English. And of course, I'm always going to use cubes with sides parallel to the axes. I'm only dealing with Lebesgue measure, so nothing more complicated than that. And just to hit the point again, because it'll be used again, is that this integral with a bar just means 1 divided by the measure times the integral of the function over the set. So this is what BMO is. BMO was first introduced in well, it was first introduced as a condition in 1961 by John and Nirenberg. However, this condition kind of appears in a paper by John on his own in not only the same year, but I think even the same journal, has a different paper on elasticity theory. And so BMO started with a very PDE idea and very in the PDE world, and it still is connected to PDEs, of course, but it's also very important in harmonic analysis, mostly because of the fact that BMO has been identified as the dual of the real Hardy space H1. So that really kind of connects it immediately to a lot of things in Fourier and harmonic analysis. So I want to talk a bit about BMO because not everybody knows anything about it. The first main point is that BMO is a replacement for L infinity. I think if you don't care about BMO, that's the only thing that you just need to think about is that there's somehow a replacement. So first of all, L infinity is inside BMO. And that's because BMO measures, you know, in an average way, how far a function ever gets from its mean on any cube or interval. But if you're bounded, your function by definition can't ever go very far at all. So it has to, on any interval or cube, never go very far from its mean because it can never go very far. So L infinity functions are in BMO. And you can show that the BMO norm is less than or equal to the L infinity norm. If you wanted the BMO norm less than or equal to twice the L infinity norm, that's very easy. It's just the triangle inequality and the fact that the mean is going to be less than or equal to the sup. But if you want the constant, like I've written here with a 1, you have to be a little bit tricky and pass through the mean oscillation with powers of 2 and then use orthogonality. But you can get, this is the sharp inequality that you can get if you wanted one. However, you might be thinking, okay, but I said that L infinity is in BMO, but it's a replacement. BMO is a replacement for L infinity, and it's because BMO is strictly larger. It's a strict subset. And the example is the minus log x. So the minus log of the modulus of x is in any dimension in BMO, but it's obviously not bounded either at the origin or at infinity. And in fact, minus log x is the most important BMO function. It's very, if you look at the John Nuremberg inequality, which I won't talk about, you see that kind of logarithmic growth at the origin is very somehow a property of how badly the growth of a BMO function can be. But logs are the examples, and I think I'm going to mention logs everywhere that has an example. And BMO is almost just, liking a lot of logs, I think, because this is the source of examples. And my work with Almut and Galia, if you decide to look at it, I'll put up the titles so that you can look in the archive. It's full of examples working out these things, because I think it's very messy stuff, and you have to kind of get your hands dirty and work with examples to see exactly what's going on. And there's some nice pictures and nice examples, and they're almost all logs. In fact, I think they are, maybe all of them have logs in them. All right. So another way in which BMO is a replacement for L infinity is because of the Poincaré inequality tells us that the critical Sobolev embedding says that W1n does not, well, by a counterexample, W1n does not embed into L infinity. However, Poincaré tells you that W1n does embed into BMO. So this is, again, an example. This is the first example of how BMO is a replacement. So something fails for L infinity, you say it's too restrictive. So the first thing I would ever do is say, oh, well, what if it works for BMO? Another example for those of you that like singular integrals is that they tend not to map L infinity to L infinity, but L infinity to BMO. So they go strictly, but they go outside of L infinity. So this is kind of like, if you don't like BMO or don't know anything about BMO, what you have to think about. I want to mention a few oddities about BMO. One of them is that if I have a BMO function and I cut it off, so I multiply it by the characteristic of some set of positive measure, I might no longer be in BMO. The example is the minus log absolute x I said is in BMO, in particular in one dimension. But if I only look at it on the positive half line, so now I'm flat and then I have my log, this thing is no longer in BMO, even though the minus log was. And you can kind of play with other kind of odd situations that might be unfamiliar to people that deal with things like LP. For instance, if f is less than or equal to h almost everywhere and h is in BMO, that tells me nothing about f being in BMO or not. An example, even worse, is you could take a function f and bound it between two functions g and h, where g has BMO norm 0 and h has BMO norm as small as you'd like. That doesn't mean that f is in BMO. And this is the kind of example. You have this function here that I said is already not in BMO. Multiplying it by 1 over k won't ever make it in BMO. And I can always bound it between 0, which of course constant functions have BMO norm 0 because they have no oscillation. And it's less than or equal to just the minus 1 over k times the log, which is in BMO for any k. And so by choosing k large enough, this thing can have BMO norm as small as you want. The moral of all this is that BMO is not about magnitude of the function. It's really about something more. It's about how the values kind of somehow play together in a way, and cancellation, right? Harmonic analysis is all cancellation, cancellation, cancellation. So the way the function's kind of values behave says how the function kind of works with its averages on every scale, and that's what tells you about a function being in BMO. So it's a very non-obvious condition being in BMO, in my opinion. So that's enough BMO propaganda. So now I want to talk about vanishing mean oscillation. This is very familiar to those that do PDE. A subspace of BMO that's called Saracen's BMO space is the set of all BMO functions that have exactly vanishing, the limit, mean oscillation. So if you take your function and you look at cubes that are getting smaller, you want the mean oscillation, well, the cubes that are going to 0 and measured, then you want the mean oscillations to go to 0. And so this is a strict subset of BMO, and it tends to have very nice properties. And the kind of main example that you kind of give is that these functions can be approximated in the BMO norm by uniformly continuous functions. BMO kind of is missing a nice dense subspace, right? In LP and Sobolev spaces, we very often have proofs where you start with a dense collection and you do everything, and somehow your piecewise linear things give you everything. In BMO, it's harder to do that because it's so large, right? It's not separable. It's bigger than L infinity. It's really got too much in it. Whereas VMO has a kind of identified nice collection that you can kind of look at first, and then see how things work under the BMO norm. Just to give you examples, the minus log, the prototypical BMO function, is not in VMO, but the log is.
And
Yeah,
you
I don't know
can
if
define BMO with respect to any measure, right?
Yes, yeah, absolutely. So even if it's not doubling, you can just define BMO by changing the measure. And you could do it on Rn or on a measure space. There are many ways to generalize this, but here there's no D, I just mean Lebesgue measure, but you could just replace this by something else, and the mean is respect to that same measure, and this average is respect to that same measure.
Yeah, okay. And so you're saying BMO is a replacement of L infinity, but L infinity sort of sits inside the family of LP spaces. So is there a replacement of LP spaces in which BMO somehow is located? Or I'm being very naive, sorry.
Yeah, no. So first of all, BMO, so if I'm just dealing with general BMO with rectangles and Lebesgue measure, BMO lives inside local LP for all P.
Okay.
So that's one thing. That comes from the John Nirenberg inequality. So it's not quite LP. It's not equal to any LP, but it lives in between L1 loc. Sorry, it lives in L1 loc by definition, but you can show that it's actually in LP loc for all other P. It doesn't really coincide with any of the LPs because it's not about magnitude, right? Where LP is all about mass. There are other kinds of spaces that are closer to the LP scale, right? There are these John Nirenberg spaces, JNP, that kind of give you in-betweens of LP and weak LP in such a way that as P goes to infinity, you gain BMO. So in some sense, this JNP scale, there are many experts in the audience, so I shouldn't say anything about them. This can kind of be like the BMO P version, because L infinity is then BMO, and these JMPs are between LP and weak LP.
Thank you very much. Sorry for interrupting.
No, not at all. Also, another thing is you can also do BMO, but looking at the P mean oscillation. So you look at the deviation from the mean to the power of P, and then you take a 1 over P, but that doesn't really give you anything LP. In fact, those are all the same space. So you might think just adding some P parameters to the BMO definition will give you something closer to LP, but then BMO would be P equal to 1, so it'd be closer to L1, so that it doesn't actually do anything. You can show by the John Nirenberg inequality, all those BMO P spaces are actually the same. So then thank you very much for the interruption, because this is all interesting things if you care about these things. So now let's talk about rearrangements. So if I have a measurable function, I define its distribution function to be the measure of these super level sets. And I want to say that a function is rearrangeable. The reason why we use that term will become clear in a moment if the distribution goes to 0 as alpha goes to infinity. Examples are LP for all P bigger than or equal to 1 and less than or equal to infinity. These are all rearrangeable functions. For P strictly less than infinity, this is true even for weak LP, just by the definition. However, when P is equal to infinity, this is also true. However, there are many functions that are not rearrangeable. And like I just said, BMO is not in LP. It's locally in LP, but it's not in any LP in general. This is BMO on Rn. So that'll just foreshadow something later on. So what does rearrangeability have to do with anything? So I want to talk about rearrangements. Okay, there are two main rearrangements I'm going to talk about. The first one is the decreasing rearrangement. It's F star. If I start off with a rearrangeable function, I can replace this function F with a decreasing right continuous function on 0 to infinity in such a way that I'm equimeasurable. So the rearrangement of my F, the distribution of my F is equal to the distribution of my F star. So I'm taking a model of F that is on 0 infinity in such a way that I'm preserving things like mass and I'm decreasing in right continuous. The picture, this is due to Almut, not me, so don't ever ask me to make you a picture. On the left, I have a nice function F. You see that it's oscillatory all the way to plus infinity. You're supposed to imagine those oscillations continuing. It's unbounded at some point. And when I take the rearrangement F star, I'm now on 0 to infinity. I'm now decreasing, in this case, continuous. And all of these solid red lines represent the superlevel sets. Well, they have the same measure in both pictures. In fact, it looks like you just replaced the superlevel sets on the left by an interval starting at the origin of this appropriate length on the right. And that's exactly what you do. You clump together these red lines, make them into an interval, and put it starting at the origin. But you can think about how this is a model in the kind of mass sense, right? The mass hasn't changed. I'm equimeasurable. So I have a model for this function on 0 to infinity. However, you're losing a lot of geometry that's going on, because here I have these oscillations that continue on forever. This tells me something about the behavior of the function. It's highly oscillatory in some sense, right? Because I have little sines and cosines. But then when I take the rearrangement, you notice that the whole thing gets stripped flat. So somehow this is F star is almost like a geometry free model of F, which is in some sense maybe a bad thing. But also in this case, it's interesting because I went from something that has high oscillation to something that's flat with no oscillation. So what does this have to do with BMO will be the topic of this talk. A second rearrangement is the symmetric decreasing rearrangement, SF, which is given by a transformation of X placed into F star, where here omega n is the volume of the unit ball. This is a very important rearrangement. What this SF, called the symmetrization of F, does is it replaces F with something that's radially decreasing and equimeasurable with F. It's widely used in geometric functional analysis. My favorite application of this is the Fabre-Cron inequality, which is very well known. I'm sure many people in the audience know more than me. If you look at the fundamental eigenvalue of the Dirichlet-Laplacian on some bounded domain, omega, then you can show that it's bounded below by the fundamental eigenvalue of the Dirichlet-Laplacian corresponding to the ball of the same measure. And so you could think of that now in terms of a minimization problem. If you're minimizing the fundamental eigenvalue over all domains of a fixed volume, the minimizer is exactly the ball. And in fact, there are rigidity statements and there are stability statements. People have studied quite a bit of this. And what does this have to do with the symmetric decreasing rearrangement? Well, it just follows from the fact that the map F to SF is an isometry on the sublevel space W12. So you see somehow boundedness properties on function spaces yield interesting geometric analysis results or techniques. Usually things that have a geometric backing to them. The reason why we have an isometry on W12 is, well, the L2 norm of F and SF are equal because I have something equimeasurable. F is equimeasurable with F star, right, by definition. And then this transformation that we do to make SF retains equimeasurability. So you're just moving the mass around, never changing the mass. So the L2 norm stays the same. If you look at the gradient of F versus the gradient of SF, then now that's a little bit different because you're looking at not so much just the mass, but also where the function's going after you move from a point. So this is the Polya-Zago inequality that says that the L2 norm of the gradient can't increase. And together, this with the min-max characterization of the eigenvalues gives you the Fabre-Cron inequality. Something related to sublevel spaces that is very interesting and to keep in the back of our mind is that rearrangements are non-linear operators. And so boundedness, anything like having an isometry on W12, does not imply continuity as a map. All right, we're used to linear operators where boundedness and continuity are equivalent. And so I have an isometry on W12 by the above. Do I have continuity? Well, so this has actually been discussed. Caron in 1984 showed that in one dimension, the sublevel space W12, the decreasing rearrangement, symmetric decreasing rearrangement is continuous on W12. However, in higher dimensions, Almgren and Lieb showed that that's not true. So somehow there's this dimensional difference and how continuity plays a role. And at the end of the day, it has to do with like the fact that in higher dimensions, you can have these kinds of like plateaus and things that stop continuity and mess with the derivative in a bad way. Clearly from that description, I don't know anything about it. But the point is that now we think about rearrangements, we have continuity and boundedness are different questions. So now I want to talk about rearrangements and BMO together. And I'm going to first start with a way in which they're completely incompatible. They're incompatible because BMO functions need not be rearrangeable. The example is the minus log x. It's not rearrangeable because its distribution function is actually infinite. However, if you chop it off, you take the minus log plus, then now you're only looking at the logarithmic branches at the origin, and then you're flat. That thing is rearrangeable because that thing has the distribution function going to 0 because of the shape of the log. So that's a bit of a problem. I said LP, they're all rearrangeable, so I have rearrangements for LP functions. BMO, that's not necessarily true. Another weird oddity is that BMO is invariant under vertical translation. So if I take a function and I add any constant, which means I can go up or down, I don't change. Why? Because, well, I mean, from the definition of mean oscillation, the fact that I oscillate doesn't matter if I go up or down, because the whole thing's going up and the whole thing's going down. So the oscillation isn't being affected. Also, if you just look at the formula, the mean cancels out the alpha from the F, and so nothing changes. But for rearrangements, this is completely untrue. If I have a positive function, I shift it up. Oh, I meant, I apologize, a typo. This is F plus alpha star is not equal to alpha star, F star plus alpha, I mean. So they don't commute. So if I take a positive function and I shift it up, the rearrangement of that is the same as the rearrangement of the original guy shifted up. But if I have a function that's non-negative, or if alpha is negative, then by going down and crossing more over the x-axis, since I'm looking at the absolute value, that flip up means that the rearrangement is quite different. So F plus alpha star is not the same thing as F star plus alpha. So there's this lack of like compatibility with adding constants and rearrangements. However, we have a bit of a saving grace, which is that there's a bit of a compatibility between rearrangements and BMO, and this is truncations. If I have, let's just say for now, a non-negative function, and I truncate it between two levels, alpha and beta, then first of all, the rearrangements commute. So if I take the rearrangement of the truncation, it's the same as the truncation of the rearrangement. And also, we have a sharp control over how the mean oscillation of the function versus the truncation works. In fact, it's the mean oscillation of the truncation on any cube is less than or equal to precisely 1 times the mean oscillation of the function on the same cube. So you have this kind of nice behavior with truncations, and this is a very technical point of our papers, but this is really the technical point of our papers in some sense, is that truncations work well with both, so that we're able to get nice things with nice constants, because we have the nice constant 1 in the truncation mean oscillation inequality there. So now I want to, what are the 3 questions of our work in general? Question 1, is the operator, the decreasing rearrangement, is it bounded from BMO on Rn to BMO on R plus? It's BMO on R plus because F star, remember, is a function on 0 to infinity. So by this, I mean I'm looking at all mean oscillation over all intervals in R plus. So is this bounded? Meaning, do I have a constant Cn such that this inequality is true for all rearrangeable F? So I'm not making, there's not enough time to make too much of a fuss, but the fact that not all functions in BMO are rearrangeable means that this inequality doesn't even make sense for all functions, right? If you take the minus log, F star is infinite, right? So is infinite a constant? So does it have BMO norm 0? Or is it infinite, so it has infinite BMO norm? Neither, right? Because we're looking at locally integrable functions here, right? So we have to always restrict to rearrangeable F. And even more interesting is, what is the sharp value Cn? How does it depend on n? So is Cn even dependent on n? And what's the growth as n goes to infinity? This is very interesting because it connects to other constants that are very important in harmonic analysis, like the John-Nuremberg inequality. You can relate the constants in John-Nuremberg to the constants of this rearrangement. And so this dependence and the sharp values are of interest. Question 2, ditto for the symmetric decreasing rearrangement. And now I'll use dn for that constant. Is there such a dn in any dimension? How does it depend on n? All questions. The third one, since I alluded to the fact that we have continuity issues, are the rearrangement operators, either of them continuous from BMO-Rn to BMO-R plus? Okay, so these are the 3 questions. I'm going to talk a little bit about them. Let's start with question 1. Before I start about the questions, there's a bit of a framework that I want to talk about. I want to talk about shapes. So notice that the definition of BMO is all about cubes. In one dimension, a cube is just an interval. And in harmonic analysis, we deal with cubes a lot. We also deal with balls a lot. And in harmonic analysis, you very often see, or this is how people do it in class and whatever, they start off with cubes or balls, and then they say, well, they're geometrically equivalent, or it's the same thing if we look at the other one. So you have BMO with respect to cubes. Then you look in a textbook, it says, well, if you take BMO, but you look at balls instead of cubes, you get the same space. Completely true. However, the idea is that you're making that change because sometimes it's easier to work with balls than it is to work with cubes. Balls have nice properties. Cubes fit together really nicely. So this fluidity of shape is interesting. And so what I mean by a shape is just an open set in Rn. I'm just dealing with Rn with Lebesgue measure that has positive and finite measure. And then a basis of shapes in Rn is an open cover of shapes. So cubes are one example, balls are another, but you can get much more exotic, right? You can look at all rectangles of with sides parallel to the axes of arbitrary eccentricity. Well, that might seem really close to cubes, but in fact, that basis of shapes has fundamentally different properties from cubes because rectangles are much more flexible in terms of where they can go, right? But you can get even more exotic. You could have the basis of all asteroids or anything like that. So then if you have a function that's in L1 over all shapes of some fixed basis S in Rn, you can define the space BMO-S in exactly an analogous way. You look at the mean oscillation over shapes S in your fixed basis, and you take the supremum, and you require that this thing is finite. This notion of looking at general shapes in harmonic analysis is completely not new. The maximal function world uses this all the time. They have lots of theories on how the shapes over which you're taking your averages influence the maximal function and how its boundedness tells you about the geometry of your shapes. There have also been connections, and people have done shapes and things like this with Muckenhaupt weights, probably because they're so deeply connected to maximal functions. So Galia and I, in another paper in 2020, it was published, started this nice generalization, and as weak a way as possible, look at BMO on shapes. Many people had done other general kind of things but with some restrictions. So we tried to be as general as possible. So this is going to be useful because this is going to be a framework in order to answer some of the questions that I had in the previous slides. So question one, let's talk about that. Known results. The first known result about boundedness of the decreasing rearrangement is due to Bennett, DeVore, Sharpley. The work in their paper implies that the constant Cn is at most 2 to the n plus 5. Okay, fine. Next, we have Klemisch and Kornowski. Their work showed that in one dimension, the constant is actually equal to 1. It's clearly bigger than equal to 1, and they show it's then less than equal to 1, so it's actually equal to 1. And that's sharp, and that's in one dimension specifically. Okay. Then Kornowski goes off in 2005, and he shows that if you're taking functions that are in BMO with respect to the basis of rectangles, that's what I mean by BMO-R, so bounded mean oscillation on all rectangles, then the F star is going to be in BMO with a constant 1 here independent of dimension. So all this to say is that somehow the geometry of the shapes on which you're measuring your mean oscillation affect the boundedness of the rearrangement operator. Because here I have cubes in n dimensions, I depend on n. But now when I go to intervals, I get something sharp. What's the difference? Why are intervals any better than cubes? And then when I go to rectangles, I still get this sharp constant 1. Why are rectangles closer to intervals, and why are they any better than cubes? So the idea is that all these proofs have to do with chopping up your domain. Okay, in harmonic analysis, we chop up our domains, either covering lemmas or Caldron-Zygmunt decompositions. You work with splitting up the domain in such a way that you can kind of get a good control of your function. And the way you do that depends on your preference, depends on what you want. In Bennett, DeVore, Sharpley, at the essence of their argument is the standard Caldron-Zygmunt decomposition. And the Caldron-Zygmunt decomposition says that you can break up your domain space Rn into cubes in a nice way, such that you have control over the averages of an L1 function. By control, I mean the averages are larger than some threshold alpha and less than or equal to 2 to the n times some threshold alpha. So when you're breaking up your cubes with this alpha in mind, you get this kind of control, but you can't do any better than that. You'll get that the average will be larger than alpha on all of your nice cubes, your nice collection of cubes that you're picking from this chopping up, and it's less than or equal to 2 to the n times the alpha. I apologize if you don't know anything about this, but if you do, you know exactly what I mean. So where does this 2 to the n in Caldron-Zygmunt come from? It comes from the fact that you're starting with cubes and you're deciding if you want to keep it or not. And if you want to keep it, you keep it. If you don't want to keep it, you chop it up. And you chop it up along the longest side, you no longer have two cubes. You now have two rectangles when you do that, right? You can't just cut a cube in half. So you no longer are looking at cubes. So if you're trying to break things up into cubes, you've failed. So do it along another side, but now you still have rectangles. The idea is that you have to take a cube and you have to cut it up n times to get then 2 to the n subcubes. And that's essentially where the 2 to the n in Calder-Sigmund comes from. Now, in one dimension, the work of Clemish and Kornofsky, they're dealing with intervals. On intervals, you have something much stronger due to the order structure, essentially, of R, is that you can break up your intervals in such a way that you have nice disjoint intervals on which you have the averages precisely equal to alpha. And this is the rising stud lemma of Ries. And so this sharpness, this is like a sharpened version of Calder-Sigmund, gives you this sharpened version because intervals are in some sense better than cubes. Now go to Kornofsky, he generalizes, you could show that the rising sun lemma won't work in higher dimensions for cubes. Calder-Sigmund is as good as you can get. But if you're going to higher dimensions and you're willing to look at rectangles, then this extra space that you get from the rectangles means that you can get a much better constant. And in fact, again, if you take a rectangle, you split it along any side, you get two rectangles. So this kind of nice way that rectangles work means that you're able to get a generalization of the rising sun lemma. And then you can show this sharp constant 1. So the slide basically should convince us now that there's a connection between these questions and these constants and geometry. So towards question 1, in a paper with Galia and Almut, we showed the following, that if you have a basis, okay, so if your choice of sets admits a Calder-Sigmund decomposition at some specific level for any L infinity function. What does this mean? Well, Calder-Sigmund decomposition, if you know what it is, that's exactly just a generalization to these shapes. C star being the constant that you get, either 2 to the n or 1. Why does it only have to be L infinity functions? That's because of a lot of technical tricks and lemmas involving truncations. Show that, in fact, you only have to check this for L infinity functions. And then, in fact, you only have to do a Calder-Sigmund decomposition at a very specific level. If you have this kind of geometric setup on your basis, then the rearrangement of a rearrangeable BMO function is in BMO with a constant exactly equal to C star, the same one that you got from the Calder-Sigmund decomposition. So using this, we're able to show the following, which is an improvement on Bennett-Devoir-Sharpley. So Bennett-Devoir-Sharpley, remember, is a 2 to the n plus 5. The theorem that I just quoted, really, you could push it down to 2 to the n, but the plus 5, who cares? The point is 2 to the n is the behavior of the constant in terms of n. However, we've shown in another paper that there's a basis of rectangles P, I'll explain it in a moment, such that the BMO norm of F star is less than or equal to 2 times the BMO norm with respect to this choice of rectangles P. So this is now dimension independent, just like the Kornofsky result was. And then that is less than or equal to 2 to the n plus 1 over 2 times the BMO norm of F. So passing through this choice of basis P allowed us to improve the Bennett-Devoir-Sharpley from 2 to the n to 2 to the n over 2. We have no idea if that's good. We have no idea if that's sharp. We have no idea what the sharp constant is or how it should depend on n. For all we know, this is how Almut always says it, for all we know, the sharp constant is Cn equal to 1 independent of dimension. I have no evidence to the contrary. But somehow this passing through this basis, this kind of framework of shapes, allows us to reduce the constant to 2 to the n over 2. Now, what is this basis P? This basis P is the collection of rectangles, again, sides always parallel to the axes, with side lengths coming from this prescribed collection of numbers. So we're looking at A is some number, and then we're looking at these kinds of multiples of powers of 2. And the reason it's called P is because it's based off of actually the A series of paper. And this basis P has this nice property that if you take it and you bisect it along the longest side, you get 2 rectangles that are still in the basis P by construction. Also, this basis P is really nice because it has bounded eccentricity. So basically, it can never get too thin and far apart. It kind of is, it's closer to a cube than an arbitrary rectangle is. So how do I prove such a thing? I've not that much time, so I'm just going to skim through it. The idea is that we want to get geometric compatibility between this choice of rectangle and an arbitrary cube. And then that kind of geometric compatibility will give us a volume ratio, and that's where these constants come from. So the first one, this 2, comes just from our previous theorem about Calder-Sigmund. We can bisect these things and remain inside that set, inside my basis, so I can replicate Calder-Sigmund and get the constant 2. But where's the second inequality come from? The second inequality comes from the fact that if I start off with a rectangle in P, okay, so it has a longest side, I can then put it inside a cube whose side lengths are equal to that longest side. So every rectangle in P can be put inside a cube. And then you can compute that the volume ratio Q over R is equal precisely to 2 to the n over 1 minus 2. And because of that, this means that the mean oscillation of F on any rectangle R from my basis P is less than or equal to that same constant times the mean oscillation on that cube. So being able to go between different shapes and having control over the volume ratio when you do that is how to go between mean oscillations. And so this 2 to the n minus 1 over 2 multiplied by the 2 that we get from Calder-Sigmund is exactly how we end up with this constant here. So now let's look at question 2. What do I know about the symmetric decreasing rearrangement? Well, you can easily show that in dimension 1, the symmetric decreasing rearrangement is bounded on BMO with a constant D1, sorry, that's supposed to be D1, that's strictly larger than 1 and less than or equal to 2. It's larger than 1 follows from examples. You can construct them. Essentially, the failure of the sharp constant 1 here is because the symmetric decreasing rearrangement is not monotone, it's radial. And that means that you're going to actually expect that the mean oscillation is going to be maximized over some some cube that contains the origin, which means that I'm no longer monotone there. So this lack of monotonicity effectively is what accounts for this difference in sharp constant. Now, how do I get the fact that D1 is less than or equal to 2? It's a pure computation. The fact that the SF of x is equal to f star of 2 modulus x. This is by definition. You get that if you're taking an interval in the positive half line, the average of SF on that interval is just the average of f star on 2i, where I multiply every element of I by 2. And then the mean oscillation of SF on I is equal to the mean oscillation of f star on 2i. And so if using the fact that SF is even, the BMO norm is less than or equal to twice, I'll tell you why in a moment, the sup over the mean oscillations if I'm only looking at intervals that miss the origin. And here, this is exactly just twice the BMO norm of f star, which we know is less than or equal to twice the BMO norm of f by the sharp constant of Clemish and Kornofsky. So this is all kind of clear, except where this first inequality. The point is that when I have an interval that crosses the origin, then again, it's all about geometry of intervals. Then because I'm even, I can kind of extend it to a symmetric interval that contains the origin. So an origin-centered interval. And by evenness, I have the functions the same on both sides of the origin. You can actually show that the BMO norm is going to be less than or equal to twice the BMO norm, but if you only looked at one side. So it comes from the fact that if I take an interval and I cut it in 2, I get 2 intervals again. So I can measure mean oscillation on the same kind of set. And then evenness gives you exactly this inequality. So how do we extend this to higher dimensions? This comes just from Clemish-Kornofsky. In higher dimensions, we're going to do the exact same thing, but it has to be a little bit more complicated because we need to now get shapes that when I have a shape that contains the origin, I can kind of cut it up in some way or something so that I remain inside my type of shape, right? If I take a ball that contains the origin and I cut it up like I would the interval, I get pi wedges. That doesn't have anything to do with balls. But we're going to see what happens. So we get this result that says that if F is rearrangeable, then its symmetric decreasing rearrangement is also in BMO with this nasty constant. And we'll see where that constant comes from. So how do I prove such a thing? Well, we have to identify now a special collection of shapes that's going to be helpful for us. It's going to be fortuitous. In the last example, the fortuitous choice of shapes was the intervals that are on the right half line, because there we somehow had complete equality between the mean oscillation. So for those choice of intervals, the mean oscillation of SF and F star are almost indistinguishable. So we had like a special choice of intervals. Here we're going to have to get a bit more fancy. So I'm going to consider A. This is going to be the basis of all balls that are centered at the origin, along with all annular sectors. Okay, by this I mean annuli that are then intersected with suitable spherical cones. We have to define, certain sectors, right? What do I mean by suitable spherical cones? But think about it. This choice A is the collection on which F star and SF are almost indistinguishable. And that's the first point. The first point is if you measure the mean oscillation of SF on any such shape and you take the supremum, that norm is actually equal to the BMO norm of F star. Because if you're the easiest to think about is the centered ball. If you have a radial function, you have a centered ball, then it really only matters the radial profile of your function, right? And the radial profile of your SF looks exactly like F star, right? Under some little transformation. So I've chosen this collection A that works very well. And then now, how do I go between A and any ball, let's say, right? We might want to end up with cubes, but now I have to go back from these shapes to balls, just like I had to go here, this 2 is the way that I can go from looking at only intervals in the right half line to this BMO norm takes all intervals, okay? So now I have to go back from the special basis A to all balls, and we'll see why balls. And so you can do this if your ball's already centered. Well, then I'm already in my basis A. If you look at the right, this is an example of a non-centered ball. Well, you can just put it inside a centered ball and calculate that the ratio of the volumes is controlled by 2 to the n. Okay, what if I were not a centered ball? What if I were a ball that was away from the origin? Now I could put the whole thing inside a big ball, but then it would be huge in comparison to the volume of that thing, because as my ball floats away from the origin, if I'm taking something symmetric around the origin, I have to get bigger and bigger and bigger and bigger, even if my traveling ball doesn't change volume. So this is why we have to look at, in red here, this is an example of this annular sector. And so you can fit this ball in this annular sector in such a way that, again, the volume ratio is controlled by 2 to the n. Okay, and then going from balls to cubes is a trivial exercise. If I have a cube, I can always put it inside a ball, and the volume ratio is going to be, it's a little bit ugly, but it's there. So now altogether, we can repeat the same steps as we had before with a little bit of extra. If I look at the BMO norm of SF, this is controlled by some constant times the BMO norm of SF, where I look at balls. This is where the constants start getting bad. This is from going from cubes to balls. But that's good because radial things, balls, you think balls are good in this situation, and it is, because the balls we can now relate very well to this choice of center balls and annuli A. And again, this 2 to the minus n kind of kills it 2 to the n. So I now have control in terms of a different constant. And now this is exactly a nice basis on which SF is related to F star. Okay, so I've gotten there. And now you can use either Van Sharpley or our improved result with a slightly better constant. And you get that this is less than or equal to a constant times the BMO norm of F. And this shows boundedness of the symmetric decreasing rearrangement on BMO. This has never been done before. Don't really know why. I just don't think anyone's ever really maybe thought about doing this. But it's interesting because these constants are so geometric. There's like so much geometry involved, even though this is a harmonic analysis, functional analysis kind of question. So I don't have very much time to address question 3, but I'll give you the highlights. So first off, I'm going to spill the beans. Question 3, in case you remember, is about continuity of rearrangements on BMO. I'm going to spill the beans. Rearrangements are not continuous on BMO. Ta-da. Here is the counterexample. If I look at the left, okay, so these are, I have a sequence of functions, which is a log piece, which is a blue piece, and the plateau, that's red. And then my sequence evolves by maintaining the plateau, but the log piece is essentially divided by k. Remember, I had a 1 over k times log at the very beginning. So now I have 1 over k times log with this plateau piece. This is a sequence of functions. It converges in BMO to just the plateau piece, because as k gets larger, these logarithmic peaks kind of go down because I'm dividing by something larger and larger. So I have a sequence of convergent BMO functions. What happens when I look at the rearrangements? Well, when I look at the rearrangements, this red piece has to get shifted slightly to the right in order to compensate for the tip of the log wants to be, because the highest values, it wants to be the most to the left. So these highest values get put to the left. I have a log piece over here. And the plateau, you see it starts at about my little hand and goes to there. So the plateau got displaced. And then the rest of the logarithmic, kind of the trunk of the tree, gets pushed over here. So what happens to this thing? Well, if I look at the limit of this, we said it's just a plateau. And so the rearrangement of its limit is just, again, itself. It's already a decreasing, right, continuous function on 0 to infinity. So now if I take the rearrangement of my fk's, of my sequence, and I subtract the rearrangement of the limit function f, then if you look, no matter how you're going to do it, you're always going to have this problem at the point 1, where the fact that I have the plateau and the shifted plateau, it's always going to be shifted for any choice of k. And so the difference is always going to have a jump at 1. And when you have a jump at 1, if you look at the mean oscillation around that jump, you're going to get like a half. And so you can show that this sequence does not converge in BMO. So, oh wait, all is lost. Well, the reason why I introduced VMO at the very beginning is because that's essentially what we decided to do is we have failure of continuity for BMO. I showed the example for the decreasing arrangement, but a similar example works for the symmetric one. So maybe going to VMO, everything will be fine. So that's the idea, is VMO is somehow a distinguished subspace, but it's also a subspace where things tend to work out nicer, where we have closer relationship to continuity, where we have dense things, where things are nice and continuous. So what we do is first we show that if we have a rearrangeable VMO function, again, not all VMO functions are rearrangeable, then the rearrangement f star and SF are both in VMO. This, I foretold the lack of time to say anything about this, but essentially this comes from the fact that the rearrangement is something so VMO functions of one variable cannot have a jump, because around that jump, I'll always have a mean oscillation of a half no matter how close I get to the jump, so I can't have vanishing mean oscillation. So it turns out that if you take the rearrangement of a VMO function, you get something that away from the origin is uniformly continuous. And so your only possible issue is at the origin, and you've localized where your problems are. And so then you can just be clever and show that if f is in VMO, then the rearrangements are in VMO. And then you could say, okay, so maybe now I can get continuity for VMO. Well, the answer to that is actually no, unless we have some normalization conditions. So if you look at our papers, you'll see examples of VMO functions that will converge in BMO, that their rearrangements do not converge. So we don't have continuity. But since we're in VMO, we're able to almost fix the problem. What do I mean? I mean is that we just need some normalization, some extra conditions to guarantee convergence of our sequence. So if I have rearrangeable VMO functions that converge in BMO, and then one of the following two things happens. Either my sequence converges not only in BMO, but also in L1, or the sequence actually converges, is positive, and it converges monotonically, pointwise, to the function, and LK, which is the infimum of f star k, converges to L, which is the infimum of f. Don't forget, in the sup of f and the sup of f star are the same, right? Because the L infinity norms are equal. But the inf might not be. An example is the one I had at the very beginning with this oscillatory piece that then got flushed out straight upon rearrangement. The min went from 0 all the way up to 1, or the inf, I should say. So we need some kind of normalization condition. And under one of these normalization conditions, then you get that, in fact, the rearrangements, either the SFs or the F star Ks, do converge in BMO. I think these kinds of things, normalization is completely natural for a few reasons. One of them is that, I said that BMO doesn't care about going up and down, right? So BMO kind of floats a bit. right? Some people always take BMO to be mod constants, and then they think about it as a space mod constants. But we're thinking about it as a space of functions with the semi-norm. It's actually not a norm, obviously, at this point. You realize this because it floats a bit. But because it kind of floats, you almost need to like pin it down in order to then get convergence on the rearrangement side, because convergence on the BMO side doesn't care. You can float a lot and have different things, and that doesn't affect the convergence. So in order to then pass to this operator that does care, you have to almost pin it down in some sense and get some normalization. And so you can do that in either just making sure that the masses also kind of line up, or I think what's the best kind of like the most obvious kind of normalization condition for BMO is the imps, especially because, you know, monotone BMO functions on the right half line actually are not only in BMO, they're also something called BLO. BLO is the space where you look at mean oscillation from the inf over any interval if you're in one dimension. So somehow this connection between the infs and monotone BMO functions just seems really like a thing. And so I don't want to say anything more about the proof, but one thing that I think is really interesting is that at the heart of this is actually a version of Artsela-Ascoli for VMO. So you can get a characterization of relatively compact subsets of VMO. This is due to Brzee and Nirenberg. Again, Nirenberg crops up the beginning and the end. And this kind of Artsela-Ascoli, right? In rearrangements, compactness arguments I use all the time. In BMO, not so much because it's a little bit difficult to use because nothing's dense and all that kind of stuff. But for VMO, we get this nice kind of characterization in terms of uniform vanishing mean oscillation condition. And I think it's just really nice if you're interested in Artsela-Ascoli. So I will leave you with, these are the two archive papers about which I spoke. They're both already there. Other than that, merci beaucoup tout le monde. Thank you very much for coming so early to listen to me talk.
Are there any questions?
I have a question. It's not about BMO. Can you hear me?
Yes.
It's not about BMO, it's about rearrangement.
Okay.
If we replace the Lebesgue integral by the improper Riemann integral, that is, we don't assume absolute convergence of the absolute value of the integral, then I wonder whether the Weierstrass universality theorem for conditionally convergent series works for conditionally convergent integrals. So if you have a function that is conditionally convergent, that is, the improper Riemann integral exists, but not the Lebesgue integral, I wonder whether the integrals of the rearrangements are universal in the sense of Weierstrass.
So what would I mean by universal in this case? I apologize.
Just that any constant, any number is the value of an integral, of the integral of a rearrangement.
Oh, I see. So I have no idea, but this seems like the kind of classical stuff that people have looked at, because rearrangements go back to the work of Zygmunt, Polya, Hardy-Littlewood, and this seems like the kind of thing that they would be interested in, right? Because series and rearrangements, in fact, rearrangements come from series of real numbers. So it's all about cricket. I don't know anything about cricket. But Hardy and Littlewood, when they wrote their paper, kind of introducing rearrangements, looked at rearrangements of series. So they said, if I have a series and I replace its terms in a decreasing way, what happens? And so they have, and somehow it has to do with cricket averages. I don't know. And then if you look at slightly later papers, and then the book of Zygmunt, for instance, and the book of Hardy, Littlewood, and Polya, they do a lot with sequences and they do a lot with integrals. And so I wonder if they might have looked at these kinds of things, because I have absolutely no idea.
Thank you. Thank you.
I wanted to ask a question about kind of vector valued rearrangements. So suppose you try to, so this comes, you know, from like, if you have an unfodder ODE, you can reduce it to a system by saying, you know, y prime is an extra variable, y second derivative is, so you add as many variables as you have derivatives. Or in PDE, you have this prolongation where you, if you have some symmetry, you prolong it to a symmetry of derivatives and whatnot. So can you rearrange the gradient in addition to rearranging the function, right? So you would need, maybe it will be an R2 valued thing, a vector valued expression. And it could be somewhat interesting because somehow oscillation means that the gradient is small or something.
So again, the word oscillation, okay,
So,
is one of those things that some people think oscillation, they think smoothness, and they think gradients, they think Sobolev spaces. But I just want to point out that in BMO, when we mean oscillation, it's very different. Like, BMO doesn't fit into its zero smoothness, right? So I just want to say this because very often I talk to people about BMO and they immediately go to BV, right? Because they think, bounded, oscillation must mean bounded variation and there's somehow some connection, right? But anyways, yeah. So I think people have looked at rearrangements, at vector valued rearrangements, and in fact they had very little success.
who looked?
I can't remember the name, but I remember then I was listening to a talk not that long after it, and the person made some fuss about how somehow when you're looking at systems of PDEs and you're looking at vector valued world, then somehow rearrangements aren't the proper tool, and somehow they had to develop other tools. So I can't remember their name. I could find it, but I think that they had some problems with then relating back to the original. So if you had the function and the gradient and you kind of rearrange both things, I think they had problems then relating the two rearrangements together.
Okay.
I think that was it, but I can't remember. I don't actually know.
Okay, thank you. Are there any other questions?
Can you go back to the last slide where you said something about Arcelor-Ascoli? I didn't catch very well what the comment was, and the reason I'm asking is that in the convexity, in convex geometry, we use this Blaschke selection theorem all the time, and it's nothing else but Arcelor-Ascoli for the support functions. So I thought that maybe there is a geometric thing in here that is going on as well with your Arcelor-Ascoli, but I didn't catch the comment.
I think actually it's not so geometric. So the idea is that because if I have a convergent sequence, then I'm relatively compact. So we want to look at, we're starting off with functions that are convergent in the function side, and we're trying to get convergence in the rearrangement side. So what Arcelor-Ascoli, this Brzee-Nirenberg theorem, says is that relative compactness in VMO is actually equivalent to a uniform vanishing mean oscillation. So if I have VMO functions, then each of them has vanishing mean oscillation. But if I have a sequence that converges in VMO, or in the BMO norm, then this relative compactness is equivalent to saying that the vanishing mean oscillation of my whole sequence is uniform over my sequence.
Okay.
And that's this. So this is really on the function side tool. So if I have these functions that converge and they're all in VMO, then by relative compactness, in fact, I have uniform control over the vanishing mean oscillations. And then once things are uniform, things are really nice. And then you're able to pass to the rearrangements, and this uniformity lets you then say something about the convergence of the rearrangements. So it's actually not so much a geometric version of Arcelor-Ascoli as opposed to the Blaschke selection theorem.
Yeah.
So it's just a way to go between the two through uniformity.
Okay, thank you. It's very nice anyway. Even without the geometric context.
No, it is
nice.
exactly. That's why I gave such a kind of en passant kind of comment, because it's just so nice, this idea of Arcelor-Ascoli in different contexts.
That's right. Thank you.
Well, if there are no further questions, let's thank Ryan again.